All right, so in this problem, what I'm going to do is I'm going to do a word problem. So what happens is that we have a pebble, okay, that we drop in a pond, right? So we're going to drop this pebble in a pond, and so this pebble is going to cause uh, ripples in the form of concentric circles. So you drop this pebble in the pond. Let's say you drop the pebble right here. So it's going to cause little ripples of water in the form of concentric circles, right? And the radius of the concentric circles are going to be r. And and these concentric circles are increasing at the constant rate of 1 foot per second. Okay, so 1 foot per second. Okay. So now the question is, so these circles are advancing at the constant rate of 1 foot per second, right? So 1 foot per second. So these people who gave me this problem are interested in knowing when the radius is 4 feet, sorry, when the radius is 4 feet. Okay, so let's see what they mean by that. So when this radius here is 4 feet, okay, so let me actually draw it. All right, so when this radius is 4 feet, at what rate is the total area? Okay, so they want to know about area now. The area, okay, they want to know at what rate is the total area of the disturbed water changing. So this is what they want to know. The total area, right, A, of the disturbed water changing. Okay, so they want to know this when the radius is 4 feet. Okay, so let's get started. This problem sounds difficult, but you know what? It's not. And I'll tell you why. Because you have already done implicit differentiation. So the first thing that we have to observe is, okay, is the area of a circle, okay, the area of a circle and the variable r, the radius, are related. And they're, they are, in this case, if you drop a pebble over here, the area of the circle, okay, and the radius is related. And in fact, because this area is changing uh, over time, it is a function of time. Both the area and the radius are a function of time. So what is the area of a circle? The area of a circle is given by this magical formula. Okay, so the area of a circle is given by area, okay, is equal to pi r squared. Okay, so this is the formula we will be using. Let me pause this because I have a phone call. All right, so a area is related to r via this relation, here a pi r squared, which gives you um, the area of a circle of radius r. So let me actually circle this because this is actually important. All right, so I'm going to circle this. No, that's not what I want. Let's see what I'm going to be using. Okay, so I'm going to use this one. Okay, that's not a circle. So you got the picture. All right, so we want to save this. We will be referring to this again. All right, so we have that situation going there. So now what I want to do is, So, so notice that these are all functions. So let me actually write this down. This is important. So these are all functions, right? So area and R are functions of time. So, I could actually step right in time. I could actually step right in and differentiate this in respect to time. And for that, of course, I am going to be using the so-called method of implicit differentiation. Okay, so I'm going to, attack this on the left with d dt, and of course, I am going to immediately have to actually go to the right. So let me actually do that. All right, so I'm going to do that. So I'm going to go. Let me actually do this. What color should I do this? I'll use brown. Why not? So we go d a dt is equal to d dt of this expression over here. Now we know that differentiation is a linear operator that moves past, multiplication by constants, like pi. This is pi here, right? So this implies then that dA dt, the derivative of a in respect to time, okay, is going to be equal to pi dr square dt. Okay, so here we are, but we have to take the derivative of r square with respect to time. Well, the derivative of r square in respect to time is going to be, well, 2r, and then I have to take the derivative of the function r. Now I'm using implicit differentiation, so it's going to become dr dt. And of course, this is an application of the chain rule in implicit differentiation. I have to actually teach you implicit differentiation if you don't know about it, but here it is. So we have then that dA dt, right, is equal to this expression, right? Okay, fantastic, fantastic. So, so they want to know what's happening when the radius, okay, is 4 feet. So what is going on? Let me write this down. So what is going on when radius r is 4 feet? That's what they want to know. Okay, they want to know that. So, okay, this is the question. Unfortunately, I had to answer the phone, so I forgot what I was doing. So they want to know, okay, at what rate is the area of the disturbed water changing? So they want to know dA dt when r is equal to 4 feet. Okay, so let's actually insert this information that we have here. Okay, so we know that r is equal to 4 feet. So let me actually go back to black. So we have dA, right, dt is equal to 2 times 4 feet, right? And now they told me over here that the rate of change, or the rate of oh god, the phone again. Sorry, I gotta pause this again. Okay, so sorry about that disturbance. So we have that dA dt is equal to 2 times 4, and now dr dt, now the uh, the rate of change of the water, the ripple, is increasing at the constant rate of 1 feet per second. So this dr dt is going to be 1, because it is changing at the rate of 1 foot per second. So I'm going to put a 1 here. Okay, so what we have just discovered, oh, by the way, you know something? I was really silly here. You know that pi? I had a pi over here. Well, that pi I forgot to bring down here. No one is perfect. Certainly I am not perfect. So I got to put that pi in there. Okay, so I'm going to bring it down over here again. So sorry, pi must be in there, right? Okay, so we have that the area is changing at the rate of, so this is going to be equal to, let me actually do it in black. This is going to be equal 2, 2 times 4 is 8, so 8 pi feet square per second. Okay, so feet square per second. So that is the rate, okay, at which the area is changing when the radius of this ripple is 4 feet. So that's the way you do this problem. I'm sorry about the disturbance with the phone, but some computer decided to call me about some new service, and of course, it was a waste of my time. But anyway, sorry about that. But thanks for listening.